Okay, good morning. My name is Ming Yao. I'm with Singularity Engineering, and today I'm happy to be presenting a short webinar on design exploration, specifically parametric design exploration. So this is a topic I like very much because I think it's usually if it's worth doing a simulation, it's worth it to for a little bit more effort do a lot more simulation because it gives you a lot more insight into how your system behaves as different parameters are changed. So this is a quick overview of the agenda today. We're going to take a look at different ways we can apply ANSYS parametric design exploration. We will talk about optimization, evaluation of trade-offs, then some maybe less used parametric possibilities like mapping of potential responses and probabilistic design or Six Sigma analysis as it's known in ANSYS. And then after that, I'll get down to the nitty gritty about what kind of things you can parameterize and how to set up parameters in a variety of simulations. So we're going to look at how to parameterize CAD, materials, mechanical simulation, CFD, and electronics desktop. So we'll cover the whole thing. To get started, I will do a quick demonstration of a simulation. Let me see here. I think I want to start something new. Okay. And once again, feel free to write your questions down in the chat window. I will keep an eye on it. Let me find that right now. That way, if you have any questions, I can take a look. Um, Okay, well, let's get started here. So this is the ANSYS Workbench environment. One of the fundamental reasons we built this is parameters. ANSYS is a strong believer since the beginning that parametric analysis is extremely important. So now parameters is involved in every part of analysis. For example, in the very beginning, with ANSYS APDL, right? The ANSYS parametric design language. ANSYS was constructed using this idea that you can parameterize simulations so you can automatically have the computer run multiple different analyses. Here we have the workbench environment, and we can start with a basic analysis. Let's say we want to do a structural analysis of a simple beam. Starting with the geometry, we can create a geometry in SpaceClaim. Um, ANSYS is also tightly linked with all the major CAD tools. So if you're using tools like SolidWorks, Creo, Unigraphics, NX, I guess Siemens NX, or Solid Edge, you can or Autodesk tools, you can bring all of them into ANSYS with parameters, with the proper interface. So let's say we want to do sort of a basic cantilever beam analysis. I'm creating the geometry in SpaceClaim, but we can, for example, specify the distance between the height of the cylinder as 37 millimeters, and this value is now, I'll call it the length, a parameter. As soon as I go back to the ANSYS Workbench environment, you can see that we now have a parameter input. Let's update this. And we can bring that into our simulation. I have some videos on Creo NX link with ANSYS on our YouTube channel. So that shows you an example of how you'd connect a standard CAD tool to ANSYS to do the same thing. If you're using standard CAD tool, the parameters will come in under each part, and you'll see an option down here allows you to specify the parameter. We can mesh it anywhere where you see this box. If I click on this, this becomes a parameter. Click on it again, it's no longer a parameter. And let's just do a basic analysis here. We'll do a fixed support and maybe a side load. Force in the X direction. And I'm going to parameterize this value as well. So now I have two input parameters: how long this beam is. Maybe we'll put it this way, and how much force is hanging off the end. Uh, then we can look at results. So deformation, stress, it's the equivalent stress. Right. So we can also parameterize deformation and equivalent stress. So these are my output parameters. When I do all of this, I will have the parameter set available here. And now I can run this simulation parametrically. So I can try maybe a 40 millimeter beam, a 50 millimeter beam, and a 60 millimeter beam with maybe 50 newtons of force. When I do update design, ANSYS will go at each stage. It will modify the geometry, remesh it, set up solve, post-process results, and produce that results over here. So we can look at the progress panel here as it fills up. So now it's solving the design point 1, which is this one. Right? It's updating the results. So it's modified the geometry mesh and solved it, and we can track results. This table is Excel compatible, so you can simply copy and paste this into Excel for further processing. You can do a little bit of processing for curves and such here, but we're going to show you some much more interesting capabilities later on. Okay, so it's done 3, and I'll just stop it before it finishes. There are many different options in ANSYS. For example, if we have a lot of design points like this, you can imagine the simulation can be a little bit time consuming, especially if my analysis are large. There is a wide range of options to send this off to clusters to run multiple design points at the same time. This makes it possible to run very large analysis efficiently. I will show you some of those options shortly here. Okay. Um, so when we look at the properties of the parameters, you can see that there is a option to run in foreground, or we can run it, solve it to a remote solve manager. Remote solve manager then allows us to submit this to a local queue, and we can execute our solution serially or in parallel. So if I have this linked to a cluster with many different cores, I can choose to run 2, 4, or 8 simulations at the same time. These require different types of licensing to enable large-scale simulations, but it really allows you to tackle very large design sets efficiently with today's um, HPC options available. So this is a standard set. Okay, so now that we've seen the ability to do these simulations, one of the first challenges people face is what happens when I have many inputs and many outputs. Typically, you can visualize data if it's in if it has 3 unknowns or 3 degrees of freedom, so we can have X, Y, Z plotted on a curve. But what if I have 3 or 4 different inputs and multiple outputs? How do I make sense of it all? It becomes difficult even if you do try to bring the data into Excel. That's why ANSYS has a whole design exploration option here. The design exploration toolset allows you to uh, really parametrically analyze the entire design range or your design space. We have, for example, a couple of options for optimization, and you can just drag and drop these into the parameter set. Direct optimization is your classic optimization approach where you're trying to find the best design. Response surface optimization first does a design experiment to sample the design space, Then it fits a response surface to give you an estimate of how the design space works. If your design space or your parametric space is fairly smooth, then the response surface is often sufficient for you to do an optimization on. If you find that you have a lot of local maxima or minimas, then your response surface needs to be tuned and you may have to use other optimization approaches. We also have parametric correlation, which lets you see how parameters are correlated to each other. There's a ROM builder that's fairly new. I'm going to not talk about that today. I'll save that for another session. And then there's a Six Sigma analysis for probabilistic design. So if we look at one of these, for example, optimization, uh, there is a few, it's highly automated, so you can choose whether you want a quick run, a medium run, or a long run. There's options for automatic optimization, or you can choose all these settings manually. For example, our optimization methods including screening, which uses a response surface approach, single objective, multiple objective adaptive optimization, or genetic algorithm, nonlinear programming, etc. You can choose to keep things. So let's set this to automatic and quick. So this says that we're going to use a screening method for 2 parameters. It's going to do 7 simulations. Then it's going to try to interpolate across those 7 simulations to try to find some sort of a correlation between the data points. If I go with a 3 or 4, it's still screening, and then medium would be a single objective, adaptive single objective, and long would be a multi-objective genetic algorithm. So quick would be a good case if you have a very tight range where you think like a second order polynomial could fit the equations, and do some basic simulation, try to find a good trade-off. A medium would be one where it um, initially does 8 samples, so it tries to sample the space with 8 uniform samples, and then it'll keep adding points and try to find the perfect optimal design. And you can start that process by assigning um, length. Maybe we want as long as possible of a beam, but then we want the stress to be minimized, and we want maximum force. So we want a long beam that has a lot of force that has very minimum stress. So obviously these are conflicting requirements. As the beam gets longer, the stress will increase. As the force increases, the stress will increase as well. And this is why ANSYS called this tool design exploration, because when you say optimization, you're often implying that there is a best design possible, whereas in design exploration, we allow you to investigate how different parameters, you can explore the design and look at how parameters relate to each other. So for that side, I'm going to pull up an old model I've done a long, long time ago. Um, this is a simulation of a solar panel array. So solar panel, let's see if I can pull up an example here. And if we follow the parameter bar here, let's bring this back up. You can see that we have parameters on the geometry block. We have parameters on fluid flow, so we're blowing air across the solar panel. We're mapping the loads for temperature and pressure onto the structure side. So we're trying to see if the solar panel can withstand a 200-mile-an-hour wind, maybe 150, maybe 100 miles an hour wind. Um, the idea is that if you have a tornado or a hurricane go through your solar farm, you won't lose all of the solar panels. So this is a multi-physics parametric goal-driven optimization analysis. So this is the shape of the model. We have, let me bring this back up here. Right. The parameters we're looking at are the panel angle. So you can adjust for the angle, the size of the support, so how thick these beams are. We're also looking at the airspeed and the heat load, so how much sun is beating down on it and what the airspeed is. Uh, the output we have is we're looking at the maximum temperature, total deformation, and equivalent stress on the structure. So you can see that it's a mixture of structural parameters and fluid parameters as well as geometry. And that's really the benefit of ANSYS Workbench, is the ability to tie all of these different types of simulations together into a unified environment and allow you to parameterize everything. So here, if we go back, we have 4 input parameters and 3 output parameters. So there's 7 parameters in total. And if we were to process the data that's generated from, for example, a design of experiment and analysis, um, a very basic DOE analysis of this requires 25 simulations. 25 times 7 sets of parameters per point results in a large amount of data. And obviously, we need tools to make sense of this data, both visually and quantitatively and qualitatively. And that's what the Design Explore toolset allows you to do. So what this does is that we start with a DOE study, and there is a wide range of design of experiments available. You can define how many points to sample. You can define where to sample. We even have a sparse grid initialization where it interactively tries to decide what the best place to sample is. Once we've gotten a good sample of the domain, we can then fit a response surface to it. Um, the the standard response surface today we use is genetic aggregation. This method will try to fit response surface using all of the methods available. So standard second order polynomial, kriging, non-parametric regression, neural network, and sparse network. Right. So I'm going to okay. So maybe we should go back to the data before. Okay. This allows us to create an expression that allows us to predict. Well, it creates response surfaces. These are expressions or equations that interpolates between all of the inputs and all of the outputs. So once the response surfaces are calculated, we can predict for any sets of given input, we can predict what the outputs are. And there's options to look at how good the fit is, you know, and we can add additional verification points. We can add refinement points to better tune the fit. The goal is to get a response surface or an equation that'll realistically interpolate between all of our input and outputs. Um, Finally, once we have this equation, it becomes easier to tackle this optimization problem. So what we can do is we can now start to define goals and objectives. For example, just like I showed before, we can potentially minimize and maximize different parameters. We can seek targets. We can have constraints where parameters are below or above or with equal to certain values. Once we have these parameters defined, it then allows us to, ANSYS will do uh, an optimization for it. The optimization options available for multiple objectives are screening and multi-objective genetic algorithm. The screening option here will pull off 2,000 designs from the response surface. So this is a random sampling. It takes very little time. So you can do 2,000 designs, 5,000 designs, or 20,000 designs, and it'll take a very small amount of time. And from that set of data, it'll try to find the sets that best fits these criteria. Um, and these are the candidates. So when I did that process, it decided that these are the 3 top candidates for our design. But more importantly, we can also look at things like trade-offs. So trade-offs are let's hide this. Are graphs like this, where we're comparing equivalent stress versus the support size. And this is fairly intuitive, right? We know that as my support size increases, um, my stress should get lower, and as my support size decrease, you can see that the minimum stress increases. And we can click on each one of these, and it'll show me what the corresponding values are, or actually, as I hover over them, it'll show me what the input parameters are. So these are showing you things like Pareto fronts, right? The back end of this particular graph shows me what are the minimum values for if I want to minimize stress while maximizing the support size. Everything else here should be filled in as well, but what we have here is a list of possible designs. There's often a knee here, so maybe people typically try to pull off designs in this area to try to have an optimal design. We can also look at sensitivities. So this shows me for each of my output parameter, temperature, deformation, and stress, what are the most relevant input parameters. So you can see for deformation and stress, the most important parameter is how big my supports are. The panel angle to a lesser extent, but airspeed has more impact on it. So airspeed and support size are the most important parameters when it comes to deformation and stress, whereas heat load and airspeed is the most important parameters for temperature. If you have a lot of parameters, this is a good way to perform a sensitivity study to see what's important. Lastly, but possibly more interesting, is this sample plot. The sample plot has 2,000 designs. Each column represents a particular parameter that can be filtered and picked through. The green lines are our 3 candidate points. So this allows us to really explore the data set we've generated. So we have 2,000 designs here, and we can say, for example, we want to use a kind of a durable structural steel, which is not that strong in terms of steel. So maybe we want to limit it. Maybe for fatigue purposes, the static stress should be fairly low. Right? So we limit it to 20 megapascals as a maximum stress. And then that also reduces the amount of deformation. But we also want to ensure that we can withstand a high wind speed. So this is 30 meters per second. This is 10 meters per second. We want our wind speed to be at least, say, 25 meters per second. Okay, and that's filters out some of our designs. Next, typically we want to reduce the cost of our structure, so we want a fairly small member size. Well, we also want to be able to withstand a fairly high angle. So let's reduce the member size of the design, and now we're left with a few designs here, and we can use this as our trade-off. So one option is, this particular design gives us it can it's a 30-degree angle, and it's at a 26 meter per second airspeed. It's able to meet our stress and deformation requirements. And obviously, as we increase the number of samples, this will get denser. So this is a great way to really explore your design, especially at the preliminary design stage. You can do a parametric analysis to span your design space and try to find some trade-offs of what's best um, for your particular case. In engineering, we rarely get an option to have a single best design. It's usually a trade-off. So here we're trading off um, how big our supports are versus how much stress we can withstand and the airspeed necessary. We don't need to have all of these as parameters, so we could certainly, if 30 meters per second was our target for wind loading, I wouldn't make this a parameter, I would make this a constant. Then we can trade off the other values based on that. Similarly with stress, the input parameters, uh, angle, wind loading, and support size. So this is a good example of optimization. We could have the computer drive towards an optimal design, but in this case, we have 3 input parameters and no real optimal design is available. So looking at trade-offs gives us more insight into how our structure will behave. Okay. Uh, Next, I'm going to talk about mapping potential responses. This is kind of interesting because this is I did a magnetic simulation for this one. And this is ANSYS AIM. So we have a magnet here and a piece of steel above. The idea for this is that oftentimes when you have magnets and components, these days a lot of electronics use magnets for placement as well as alignment. So knowing the forces, torques of each component of the component um, as a function of the position becomes very useful. If you know the force and the torque applied to this component at every given location in the space as related to this magnet, then you can understand how much force and is being applied to it, and what you can do to how well it'll do as a fastener or a uh, either fastener or a alignment system. So here we can look at the simulation. Simulation is completed. I have the force in the x, y, and z direction as a function of this magnet, and I can calculate the torque in the x direction. We can also look at the magnetic field vectors. Let's take a look at the B field. Right, so you can see this is the magnetic field lines as around the magnet and hits a piece of steel up above. Okay, I should simplify our video a little bit here. Yeah, so that looks better. When I have a lot of vectors and it's put on this enhanced display mode, sometimes it slows down the computer. But the point here is that AIM is also built on the Workbench framework, which means that it has access to the full set of design exploration capabilities. The parameters I put here is the radial and axial distance of the steel plate compared to the magnet. We're tracking the forces here. So a quick analysis here, where we do a design of experiment. ANSYS runs 9 simulations, which is sufficient to characterize something like this. We get a set of data, and then we can look at a response surface. So we can do a 3D response surface of the force. Let's see if we can line it up properly. Right, so that's the force in the y-axis. We can look at the force in the x-axis and z-axis. We can certainly increase the amount of points. The values change dramatically here. Um, so you can have this type of data. And this will then allow you to simulate, you can predict the behavior of the plate at any location in the magnet. There's an option here to export the response surface as a functional mockup unit. So FMUs is an open source database that describes a set of data. So it's basically a lookup table type of system that lets you put any input in based on oops, based on this response surface and get the appropriate output out. So rather than interpolating data by hand, you can create an FMU directly and put this into your simulation environment. ANSYS we have our own twin builder simulation environment for system level simulation. Let me bring that up here. So what I did was I generated this magnetic force FMU. Let's see if it's a text file or right. So it's a binary file, so you can generate it and not have it be exposed to other people on how it works. Then you can open up a tool like ANSYS Twin Builder. ANSYS Twin Builder here This is the FMU. We can add a subcircuit, an FMU component. You can see we have options for a lot of other simplified system level simulation. So we can add Simulink, MathCAD, Maxwell, RMXpert, mechanical IcePack state space model. But here we're using a simple FMU here. We can have a couple of inputs, a sinusoidal function. Right. So one of the input is the radii location, and the other is I think this one is the position, um, the kind of tangential position, and this is the axial position of the plate. We have output here for the XYZ as well as the rotational degrees of freedom, and we can do very quick analysis, transient simulation of what happens if I move my steel plate in a sinusoidal fashion uh, near the magnet. Running a simulation here, so it's fully transient with millisecond or microsecond accuracy, and it'll run a transient simulation interactively here. We can add masses to it. We can add stops and all kinds of other system level functions. There's a wide range of system elements available. This tool also hooks up with um, I'm forgetting it right now, but it's uh, not VHDL AMS models. It hooks up with a large set of open source models for this type of system level simulation. So this is called the ANSYS Twin Builder, and the idea here is that we can create a functional mockup unit of a system like our magnet here, which is just a force as a function of place position. Then we can export this into as a FMU, and you can put it into your system level simulation tool and use it however you want. This can be used in MATLAB, Simulinks, and a variety of other tools. And this allows you can then model and mock up an actual system to see as you move things around how much force displacement the user will feel and whether it's going to click into the right place or not. Maybe even put in some control systems to adjust the electromagnet and control the location of this whole system. Okay. So that's a nice feature that we've been working with for a while with a number of companies on the magnetic side. And it's also applicable to a lot of different control system design as well as actuators. Right? If you have electrostatic actuator, a magnetic actuator, you can define the force position plot for the entire domain and then use the simplified model to try to control your actual system. The last thing I want to talk about in this section is probabilistic design. So far we've looked at the simulation using parameters to explore the design space, to export a response surface as a functional mockup unit. In this case, we're going to look at sensitivity study or Six Sigma analysis. Um, Six Sigma analysis allows us to specify a parametric parameter and give it a probabilistic distribution. So this is used for things like stack up tolerances, or when you have devices you want to manufacturing tolerance issues. Here, for example, I have a press fit. Let's line it up here. You can see my liner overlaps my outer sheath a little bit. The amount of press fit is really important because obviously even a small amount of press fit can generate a very large amount of stress, both on the liner as well as on the side. So this is my current press fit equivalent stress. You can see where the maximum stress is. Safety factor, we have a couple lines here where we have very low safety factors. So these are areas that could potentially fail. So adjusting for the right radius as well as the right amount of press fit to get a good grip between the two parts but not induce failure is very useful. Um, what I did here to parameterize it was I specified geometric parameters for the press fit. So I have an insert parameter and a case parameter. The case has an inner diameter of 10 millimeters, so I started with 10.1 millimeter to 0.1 millimeter of overlap. Then I also parameterized the radius, the inner radius, to see if that can help to relieve some stress. From there, we can assign equivalent stresses to we're calculating the safety factor, deformation for the insert, as well as the total deformation maximum. Then I attach a Six Sigma analysis. So assume that I have some control over the um, the manufacturing of the both the insert and the casing here. I have a wide range of probabilistic distribution functions available: triangular, uniform, normal, truncated normal, exponential, Weibull, logarithmic. So I'm using truncated normal for all of these, assuming that if the manufacturing tolerances are too large, I can screen out the ones that are outside the bounds. Um, so that's why it's truncated here. I'm using truncated normal with a mean of 10.2, truncated standard deviation of 0.1, and I'm truncating at 10.05 and 10.3. So the probabilistic distribution function looks like this, and the cumulative distribution looks something like this. This is done for each one of these. This is just a made-up case, so I didn't really follow any particular uh, uh, case study for these values, but the idea is to show that we can put different types of probabilistic distribution functions in. ANSYS will then do an analysis and create a response surface. From that response surface, it will start to sample based on our probabilistic distribution function. Right, so these are the simulation cases it ran. So it ran a total of 15 simulations. It generated a response surface, and from that response surface, it can put in it can calculate for each point what the probabilities are. And these are the probabilities that we've assigned the buckets for each of the input parameters. And from that, it'll calculate the probabilities for the output parameters. So let's take a look at our goodness fit. With this type of analysis, typically the tolerance is fairly small, so you don't have a lot of um, scatter. It shouldn't have multiple kind of maximum points. We could have added some verification points and look at the 3D plots of what this looks like. This curve is a little bit bumpy, so we probably should have ran a few more simulations to refine this curve and get a better data. But you can see you have all of this data available to look at how good the fit is. From there, you can look at the Six Sigma analysis. And all this is doing is that it's looking at each of the input plots to show you that we did indeed capture the probabilistic distribution function fairly closely. And from that, we can look at the outputs. This tells us what the probability is for, in this case, maximum stress exceeding 800 or 700 megapascals. Right. So down here we have a few that are very high stress and has a probability there of 0.0002. So 0.02% of the time you can have very high stresses. And we can check this for each one of the probability values here. There's a significant spike down here for the whole time. So this one may lead to possibly not enough friction to connect the two parts together. So we can also take a look at the sensitivities. So for each of the output parameters, this looks like the biggest one is the most important part is how big my insert is. This is far overwhelms anything to do with the case or the radius. So the radius was much less important than we initially imagined. The amount of insert tolerance is really important. So from a manufacturing perspective, this tells us that the insert needs to be controlled to a very tight tolerance, while the other functions, other parameters are of less importance. And once again, this is a Six Sigma analysis. So we've gone through optimization, response surface, Six Sigma analysis, and even exporting a FMU from response surface. I'll try to put together a ROM discussion later on because I think that's a very interesting topic as well. Okay. So that covers the different applications of ANSYS parametric design exploration. Next, let's talk about what can be parameterized. So I'll give you a quick demonstration of all of the different areas where ANSYS can parameterize things. For example, in CAD, typically, if you're using a parametric CAD tool, any parameters or dimensions you define can be set as a parameter. ANSYS has a nice tool called SpaceClaim. This allows us to parameterize, for example, the radius here. That gets set as a parameter, so we can say this is my radius. We're also able to detail the plot. So we can set dimensions, and as you set dimensions, there's options to assign a dimension and specify that as a parameter related to other things. So there are many ways to define more complex parameters in SpaceClaim. There's some tutorials on this. I don't think let's see. So this is a dimension. When you create a dimension as a parameter, there should be a little star beside it that you would click to assign this as a parameter. I don't see that star right now, so maybe I'm not assigning it quite the way I'm supposed to. So certainly geometry can be parameterized. Next, we can take a look at engineering data. So engineering data, anytime you see this P with a little circle, that can be parameterized. So we can parameterize the density. We can parameterize, for example, the Young's modulus. If you have a value, and once you parameterize it, you can see that you can no longer change it. It can only be adjusted from the parameter set. So you can adjust the Young's modulus here now. Sometimes you may have tabular data. So let's say this is at 20 degrees. At 30 degrees, we'll say it's a little bit softer. Okay. Once we have this, you can see that we have the option of still parameterizing this by parameterizing either the offset or scale. So you can scale the values up and down on the curve or offset it up and down on the curve. So even temperature dependent properties can be parameterized for analysis. Once you get into tools like mechanical, um, anytime you see a empty box, this can be a parameter. So for example, the volume and the mass can be parameterized if you're trying to reduce the weight of a part. Connections under contacts, there are various locations, frictional coefficient, offset can be parameterized. You can even add commands to it, right? If I have a command, a set of APTL commands, input arguments can be parameterized. You just have to use arg1, and you can specify arg1 is 10. That can be a parameter. Then when you set your APTL commands, you can put that argument 1 in, and that'll be a parameter that you can then adjust. If you have output parameters, that can also be parameterized. So if we put a command in the output side, when you run the simulation, there's an option to assign parameters. Oh, here we go. Right, output search prefix. So if you define any parameter with my output, right, this is now a result parameter that you can parameterize. So you can go through an entire simulation and just put whatever output of interest in APDL form, assign it to a name, and that will then, with the my on the front, that will then be an output parameter. All of our loads tend to be can be parameterized. So this is a remote point. You can see that there's a lot of open boxes here. Um, and all of the results can be parameterized as I've shown earlier. So this is what you can do on the mechanical side to parameterize various things. In AIM, you can also parameterize data. So outputs can be parameterized by clicking on this pull-out arrow and clicking on the P. On the physics side, here we can, the material assignments can be parametric. So if we want to parameterize the kind of magnetic coercivity, that can be a parametric. So you can try to decide how strong of a magnet you should use for simulations like this. Um, on the CFD side, let's see if I have one of those open. Let me open up a CFD example here. All right, so this is a CFD example of a microfluidics droplet generation. I think I have a video on this, but you can specify various parameters from the geometry to the simulation itself. Once it gets going, we can take a look at it. The point I'm trying to make is that in ANSYS, we try to make everything very easily parametric. Right, so this is the ANSYS fluent simulation. You can parameterize the geometry and mesh as we've shown earlier. If we open up Fluent, we can add some parameters quickly. Instead of anytime when you assign a value, instead of assigning a constant, you can specify a parameter instead. And this is all obviously in the help menu. So if you have any questions, welcome to dig around there a little bit, and you should quickly see um, what the values are. So here, the velocity, you can see instead of putting in a constant, you can put in an expression, which is the new ANSYS CFD expression language, or you can put in a new parameter. So I have defined two parameters, oil inlet velocity and water inlet velocity. The parameters are shown below here, and you can look at your parameters. Right, so I have two input parameters, no output parameters, and we can adjust the parameter, see what the current value is. The parameters are driven from the workbench level, so you don't need to adjust it in the Fluent GUI at that point. We can also create parameters in CFD post. You can create parameters in Fluent. CFD post in this case has a nice FFT function for what we're trying to do. So this allows us to parameterize some of the charts. So it's going to load in a chart sequence here and shows us a maximum for the frequency as the frequency of the maximum as well as a PSD of the maximum. Uh, in here, in CFD post, any expression you create can be parameterized. So here we have a little script that automatically calculates maximum amplitude and frequency from this FFT set of results, and that allows us to set this as parameters, and you can use them just as before in design response surface and design of experiments. And finally, in electronic desktop, so if you're using, I thought I had that open. Yeah, let's open this. So lastly, we're rolling a lot of these capabilities into the ANSYS electronics desktop environment as well. Obviously, parametric analysis has been with HFSS, Maxwell all along. If you like Design Explorer, adds some additional capabilities. It's very helpful, and it enables you to do multi-physics types of analysis. So let me find. Um, all right, here, this one. So this is a waveguide termination simulation in HFSS. So right now you see there are no parameters here. You can open up electronic desktop. Electronic desktop, just like Fluent, allows you to quickly change any constant into a parameter. Okay, so we have some excitations. We have, for example, we can adjust the size of our coarse glass. Let's grab the box here. Right, instead of 10, we can just say X size, right? And that turns this into a parameter. Then under optometrics, we have the option of including this as a parameter. And all of a sudden, when we do that, it becomes available in Workbench. So now we have a parameter that controls a value, any constant that can be adjusted in HFSS. A lot of things open. Okay, here we go. So that's the input parameters. There are output parameters as well. So for example, S11 here, we can create the, let's see, calculations, set up some calculation. We can specify S11 as a parameter, maybe Y11 and Z11. So we have the SYZ values as parameters. And if we go back to Workbench, now I have three parameters, one input and three output. So from this, we can now do a coupled thermal electromagnetic simulation or coupled electromagnetic structural simulation, along with the optimization, response surfaces, Six Sigma analysis, a lot of advanced techniques for data processing of large sets of data that you can generate in these simulations. So that's all of the examples I wanted to do today. We have a more advanced set of tools for parametric analysis. OptiSlang is a partner of ANSYS. So, and the big benefit of OptiSlang, which I'll pull up on the screen here. Right, so ANSYS OptiSlang is a tool from a partner, and what it allows you to do is that it does all of what I've shown here, but it's a lot more feature rich. It gives you more control. It has very advanced DOE studies that allows you to interactively adjust the data to try to get the right DOE process going. It also allows you to integrate multiple tools. So ANSYS Workbench tools primarily works really well with ANSYS. OptiSlang allows you to connect different simulation tools together with ANSYS and do advanced analysis. So if you go through the ANSYS tool set, and this is included in almost all of our licenses now for free. So if you have ANSYS tools, there's most likely you also have access to design exploration. If you go through it and you find things that you want to do but you can't quite do in Design Explorer, we would typically recommend OptiSlang as the next step up to enhance your design exploration capabilities. That's all I have for set up for presentation today. Hopefully this was of interest. I see there's a request to share model. I will try to share as much as we can. We're kind of busy these days, so I'll try to get them on our website as soon as possible. I probably won't be able to share all of these. I'll try to share some of the, maybe one example from each. so that you get a feel for how parameters and design exploration can help. And if you have interesting problems, let me know that deals with design exploration. I'd love to find out how people are using it. I've seen a few cases where people made extremely good use of this over the years, and it became really powerful for decision making on a system level. But obviously, this is something that we at Singularity and ANSYS in general feels like it's underused because it's a very powerful tool that should be more widespread. So let me know if you have any concerns or thoughts. And uh, thank you for attending the session. Feel free to visit our website at www.singularityeng.com and have a good day.